Any questions before we start with the lecture today? Anything related to the previous lectures? Any questions about?
Is there any chance you could go through like the top hat exercise?
Yes, we will for today or the previous one.
Uh, the one about like cylindrical coordinates or whatever.
Let me see. You're
I
talking
think,
about the one that is due today?
yeah, the one that's due today.
Yes, I will do that. How about you?
Uh, yeah, my question is also about the homework.
The a homework or exercise?
The homework.
Okay,
The second question, the two vectors mentioned in it, are they three-dimensional or two-dimensional?
let's discuss that. So, what we have in the homework, what does it say about the two vectors?
It says two similar than parallel to the x-axis.
Mm-hmm. And then what else did we say about the vectors in general when we try to, when we have, let me write here so you can see it. I will write here and I will erase it. So if you have two vectors like this, okay, let's assume this is the xy, whatever you want to call it, the coordinate system. And then you have two vectors, A and B. What did we do here in class when we tried to do a dot or a cross product, or a sum, or to add or subtract? We brought the vectors to start at the same point, or to connect at the same point, all right? Because if a vector is like this, so let me in fact erase this one, the coordinate system, so I don't confuse you. But if you have these two vectors here, and let's assume that this one is the red vector, just to differentiate this one. No, sorry. This one, red. Okay, so you have these two vectors. And I'm asking you, first of all, to add them. What would you do first before you add them? What did we say?
You were just looking at the diagram, you put the end.
We have to translate one or another so they come to a common point, all right? So I can take this one here and move it there. Okay, that's what I would do. Do we do the same thing about A dot B? Or for anything, A, let me start here, A plus B, or A minus B, or A dot B, or A cross B, you will have to do that. Otherwise, you cannot talk about the things that we discussed. And in fact, translation in a vector does not change anything in the vector. The vector is the same, the direction, the magnitude, all right? So by just translating the vector, if I take, say, this line here and move it there, the vector is gonna remain the same, okay? So practically, this vector here and that vector there are identical. I can take a vector and move the vector everywhere that I wish to move it here, as long as it is a simple translation. I can move it here, I can move it here, I can move it anywhere. It's gonna be identical. So now what I do to perform these operations, I move the vector here, as I have done. So I will remove this one. Okay, now I brought two vectors like this. What do you remember when I have two vectors like this? What do they do? They define one plane. Always. Two vectors that are connected at one point define one and only plane. So if they define one and only plane, and if summation and subtraction and dot product is all there on that plane, then what is the answer to your question?
It's that they're defining a plane, they're only accessible.
Two.
To,
If they are on a plane only, and the A dot B that I gave you is only on that plane, then why would I go to 3D
only for cross product, right?
for not the dot product?
Oh, right.
Yeah,
Yes,
because the dot product is a scalar.
yes.
So A plus B, A minus B, and A dot B, dot,
All two dimensions.
only in 2D. Unless you have a third vector, but if you have two that define a plane and a third out there, then you need 3D. All right, because only two define a plane. So you work always on the plane of the two vectors for these three operations. And in fact, the A cross B, you know, it's perpendicular. So sometimes people will even, in that case, will work on one plane and then understand that the direction is perpendicular. I mean, you just try to simplify your life, all right? Why would you go in 3D if you can work in 2D? Remember what we said? The key, in this class, you are gonna learn to do that. We are gonna learn on how to simplify things. Why is that? That's fundamental. Because if you don't simplify things, you will never be able to solve a real problem, all right? We always simplify. We go down to fundamentals. And, you know, if I can do 1D and solve my problem in 1D, let me tell you, I'm gonna go to 1D. Even if I could go into the computer and put 3D. It's a waste of my time. And you don't understand much if you just go directly to the computer and do. You don't understand the fundamentals. You don't develop that intuition. Intuition in engineering is fundamental to our work. Do you know an engineer who is a good engineer without intuition? No. No. It takes a long time. I'm not expecting you to develop that, but these are the experiences that will help you develop intuition, plus your work. Any questions? Other than that? Okay, let's go. If I am okay with the, let's go now to, and talk about this.
Professor,
Yes.
would it be possible for you to turn your camera on?
To do what?
Just in case you point at the board or something. If not, it's okay.
The camera is on, but I have captured the screen. So either you're gonna see me writing on my screen, because if I write on the camera, you cannot see it. If I write on the board, you will not be able to see it. So I'm using my iPad where I can write and see that. Okay.
All right, that's fine.
If I turn on I can turn something else, but you're not gonna be able to see what I'm writing, and the board is not gonna be helpful.
Yeah, that's okay.
Yeah. Okay. So you want me now to go to the Zoom, all right? In fact, not to Zoom, excuse me. I said that is not the one I'm looking for. Howdy. In fact, howdy. Go back. Okay. Let's go here. That's a top hat. And we are going to exercises. That's what you asked me, all right? Exercise 2 coordinate systems. So I will unassign it. Okay, let's talk about this. What is the question?
I was just confused when they were together in one. And I don't know. I was just confused with the notation of the vector.
Okay, what I would suggest, let me do something because I would like to solve this problem. because it was part of our lecture. What if you can come to my office hours on Sunday and I will solve it? And on office hours on Sunday, I'm not going to only solve that, I'm going to solve all of the exercises and the quizzes and then the last quiz, not the one I'm going to get today. How about that? Would that, so we can move on today. But I don't want to miss the opportunity to solve these problems. I will do it on Sunday, all right? And I will send an email to everybody who may want to join us for that. Okay.
What time are your office hours on Sunday?
1 to 3.
Okay, thank you.
Sit in Zoom. If you go to Zoom, that's the most updated times. If you have any questions about any time about anything, you go to Zoom. And let me just make sure this is not your Zoom. That's the Zoom of the other class. Okay, you go to your class, you go to Zoom. And these are all the times, you see? So Sunday, 1 p.m. You see that? It's the second. Okay. Going back now. Going back, get rid of this. There. You get rid of this. And now, in fact, I want to just go back to this one. Okay. Now, this week, you need to remember, we do a review, but it's not going to stop there. All right? We have seen those things, and we are going to see the same things throughout the class. That's why we don't spend an enormous amount of time on things which are complex. I agree with you that they are complex things, and because we're going to use them throughout the class, you're going to see them over and over again. But the reason we are going through this is so we define, again, the operators, we make sure that everybody has seen those, and we start from there. But I'm not going to assume that you, after this lecture today, you really know everything, because these coordinate systems going from one to another, it's tricky and it requires practice. So we're going to do that through this class. But I wanted now to help you also understand why we go into the trouble and penalize. It's like you hit yourself on the head every time. It's like you have a whip and you whip yourself. Why do you do that? I mean, we would not do it if we do not have a good reason. And you remember what I said, that math is an advanced language for scientists, for mathematicians, for engineers to be able to accurately describe what is happening physically. So you will see that this language, the mathematical language that looks kind of weird, is something we are using in real life without saying it. So I will bring you some examples, all right? So this inverse delta, we call it the del. But when the del, and the del by itself is a vector. But when the del is utilized, so it's an operator, because by itself does not mean anything, all right? So operators are entities which we use in mathematics. They don't, however, mean anything by themselves. So the del by itself is nothing. When the del operates on different entities, then it changes its name. And when it changes name, then it becomes, together with the function on which it operates, then gets meaning. So the gradient. When do we call del the gradient operator? When it performs on a scalar. Only then we call it the gradient. And we call it the gradient of the scalar function. So temperature is a scalar function, all right? Humidity is a scalar function. All of these quantities that do not have direction, they vary with respect to their position, where they are in physical space, and with respect to time. So they are variables. In fact, they change their values over time and in different locations. Okay. The del is a specific operator that applies to the location, not time, to the physical location. So in fact, because it involves derivatives and it is a vector, all right, as an operator, when it applies on a scalar, it creates a vector. So the gradient of a scalar is a vector function. And then you can see that here, all right? And what does it do, as a matter of fact? It does have, as elements of these vectors, as components of this vector, the derivative of that scalar along that specific direction. So at some point you understand, yeah, I have temperature, which is a scalar, but temperature in a space like that, if I had a thermometer or another thermal sensor and I would go around every now there will be stability, but because we are people distributed, every time somebody comes close to us, the temperature is going to go up, all right? Unless there is an air conditioning with heat, and that changes. But there is going to be variation in the temperature in this room. And the gradient of that temperature will give us how the temperature varies along the different directions. How does it vary vertically? That will be theta t, theta z, if z is the vertical direction. How it varies with respect to x and y is going to be exactly how it varies because of us sitting, because of the tables and the whole thing, all right? So that is the information that is giving us. And this one primarily is used, have you seen every morning when people go into the news? Maybe not here in this area because the weather is pretty good. But when I was living long years back, my kids were in school and we did not have these types of devices. Every morning, especially in grade school, they would wake up, turn on the TV when there was snow, and they were hoping for a snow day. So, and then you would see where the snow is going to be and you know how the temperature is going to go down and the whole thing. And all of these maps that we see are the gradient of the temperature. That's what they plot. Okay. So what I did here, which I think also, it is in the book. But the one thing that I would suggest to you, I was doing all the time, I still am, I still do this now for my work. When I have important things that I need, that I don't remember anything by heart. Let me just tell you this much right now. I cannot even memorize a poem. But I do remember processes because there is reason in the process, all right? So, but I do remember that. If you ask me to write on the board any one of these by heart, I will not be able to do that. That's not a shame, all right? Because we have access to them. However, what I do when I work, I write them all together and I have them available. And I do this for you, and eventually I will try to create a table. But until I do that, here is what I have put in rectangular frames. Now, of course, the X, Y, and Z is very simple. It's there. This is for cylindrical coordinates, this one. Cylindrical. And this one here is for spherical. I think you need to remember those because you will find it very useful. They are in the book, but you have to go pages, all right? And then you have to slow down and see what you're reading. And everything, all of this is in the book. But it's good for you to have them available. Not because I'm gonna ask you to do anything closed books, but even when we have your homework, your quizzes and everything, it's easy to have things available, not try to go through the tons of pages. Okay, here I'm doing a simple example, just as an example to see. Let's assume that the problem says the following. I know a function, which we are going to do a lot of times. You remember what I told you, that a lot of times when you have a charge or an antenna, which is many charges, but all clumped together. If you have that, those generate a field. If you have one charge, for example, and generates a static charge and generates a field, the best way to describe that field is in what coordinate? If you remember. Spherical. Because there is a spherical symmetry. Every problem that has a particular symmetry, we take advantage of it. Do you know why? Because symmetry simplifies the solutions. So when I have a charge, every solution you're going to find about the field that is generated by this charge is going to be in the spherical coordinate system. And then let us assume that I have 3 charges, which we are going to get in the next chapter next week. 3 charges. And then I ask you, the charges are like here. Let me add a page just to show you. Let's assume now that you have 3 charges, one here, one there, and one there. And I'm giving you these 3 charges in reference to one coordinate system. And I say that this charge is here, Q1. This charge is there, Q2. This charge is there, Q3. And then I ask you to find the total field. And I'm saying find the total field. And of course, if I say find the total field, the first thing you need to remember is how am I going to place my coordinate system? So I may help you with that and say find the total field of this right at the center of the coordinate system, which is this one. So how are you going to solve this problem? You know the field from each of the charges, but where is this field? Is in a spherical system. And what spherical system? Not one, but a spherical system for Q1 that centers at Q1. For Q2, the one that centers at Q2. And for Q3, the one that centers at Q3. So I will have to take these different expressions, and then I will have to work with them. I will have, first of all, to sum them up. Am I going to sum them up before I do any transitions, any translations? No. Or transformations, I should say. No, I cannot sum up 3 expressions that are described in 3 separate coordinate systems. I have to bring them to the same coordinate system and then sum them up. And my coordinate system is a rectangular. So what would I have to do? I would have to transform them into rectangular and then sum them up. Other times, instead of a summation, let's assume that I ask you to find the curl. Okay, let's assume that you have 3 wires. You're going to see that problem. So you have one wire like this, going like that. Okay, and that is not a Q, but it's going to be J1. And then it has a current J1. And then you have another wire that goes, let's assume to make it simpler, they all go to the same direction. And then that one is J2. And then a third wire that goes here like J3. Okay, and now I'm telling you, find the magnetic field or find the curl of the magnetic field or something, all right? But yes. What's that?
Which direction is the J3 going?
It could be up and down. I'll make it up. Okay. I'm going to find the field, magnetic field in each one of them in terms of the cylindrical coordinate system that is attached to every wire. Well, how am I going to find B, or how even am I going to find the curl of B? Well, I will have to do 2 things. Either because the curl in the curl, if I wanted to find the curl of the total field, so practically I will have to find this. Do you agree? And because the curl is distributed, so it's going to be this one. So there are two ways of doing this problem. The first line shows you the first way, the second line shows you the second way. The first line tells you, you take the three fields, which are in cylindrical coordinates and they're separate, then you translate those into the same coordinate system, X, Y, and Z, and then you sum them up. And after you do that, then you apply the curl in the Cartesian coordinate system. All right? So you bring them to the same system and then you do the curl. The other approach is to do the curl in each of the cylindrical systems, find whatever result you find, and then you take that and you translate each one of those from the individual cylindrical coordinate systems to the same Cartesian. All right, so there are two ways of doing that, but you don't, it depends what way you're gonna select, depends on the expressions and the problem. I was gonna select the one that is simplest, but that's what we always do. But in any case, in all of these problems, you will have to perform not only a translation from one coordinate to another, but also in addition to that, like in this problem, you will have to perform an operation, like in this case is a curl. All right, yes.
What's the curl supposed to be again?
The cross is the curl.
What?
The cross, this one. What did you say?
The curl is with,
The curl, if you remember when we introduced the curl, like when we did the cross, the curl is called the cross of the del. I mean, so the cross product is a cross product between the del operator and a vector. So in any case, this one, I wanted to use it to show you here, in this particular case, I wanted to find the gradient of a function that it was expressed in a cylindrical coordinate system, and I wanted to transfer this gradient into the Cartesian. So what I did, I took the function, I did the curl in the Cartesian system in this case, and then after let me erase this, I don't need this. And after I found this gradient in the Cartesian, in the cylindrical system, after I found that, then I transferred the whole thing in the Cartesian system. Okay, and that shows what I got. Now, they're long, they're not like one-liner when you write it. However, the process is not very difficult. If you follow the process and you know just the fundamentals of algebra, you will be able to solve a very difficult problem, but it's always about how you approach the problem. That's the most difficult thing. Before you take the pen to write a solution to anything, you have to think how you're gonna solve your problem. All right, do you remember that? You should always remember this, because I know that people are anxious and they do two major mistakes when they try to solve homework or a problem or an exam. They don't read the problem very carefully. They read it very fast and then they try to go into the solution. No, mistake number one. If you read the problem very fast, you miss a lot of points that will be extremely important to help you solve the problem. A lot of times when people come to me and say, how do I do that? I say, go back and read what the problem says. A lot of times they give me answers to the wrong solution, to the wrong questions. So you read it well. The second, before you start writing stuff, think on how you're gonna solve your problem. What kind of approach you're gonna take, all right? Think how people build a house. They don't build a house. When they say I'll build a house, they don't next day go there and bring all the wood, and they bring all of the cement and everything, or whatever, the ingredients to make the cement, and then they start building without plans. Who is doing anything without a plan? We need to do the same thing. We don't. We get anxious. I was getting like that. Anxious all the time to get the result. And then you start writing. I learned it out of experience. And you think that there is no book about it that tells you that. And even if there is a book, you have to experience it yourself to learn how to take tests. You don't waste time when you spend a few minutes to read it well, write down what is given, so you understand it and what is the question. And then you think how you're going to solve the problem. You're going to get the solution quickly. Unless, of course, you don't know how to even approach it, that's a different story. But if you have been prepared, you will be able to solve it. So don't worry about many lines of writing things. Usually I am very explicit because also it's very easy to make a mistake when you try to do things quickly. So for me, I'm always there. So we talked about the gradient. The same del operator, when it applies like a dot product, as I have it here. And of course, since it's a dot product, it's going to apply on a vector. So the del operator, when it applies with a dot product on a vector, it's called the divergence operator. Okay? What does the divergence operator do? Let's assume that you have a vector, a vector field D. And I want to find the divergence of it. Okay? What does that do? It really creates, when I take a del, which is a vector, and I apply that in a dot product with another vector, what will the result be? A scalar. Remember when we take these two vectors and we have a dot product, they always create a scalar. So as opposed to the gradient, which is a vector, the divergence is a scalar. And what the divergence do? The divergence finds for you the combined effect of the change, the combined changes of a vector. So if I have a vector like a field, and the field changes this way along the x direction, a different way along the y direction, and yet the y direction, and then yet a different way along the z, what the divergence does, the divergence takes all of these, the measure of this change, sums it up together and creates one number. So this number is a little tricky because it does not, like the gradient, tell you, it does not tell you specifically on how it changes like this, it changes like that, and changes in any other direction. It gives you the total change. All right? Now, I will give you an example because that is a very important observation. And why it is important and why we use the divergence very extensively is for the following reason. And we learned that from nature. Now, of course, in electromagnetics, before I go to the example, so you can relate things to see that we really do this without really knowing that it's called divergence and without knowing what exactly we are doing, all right? We're doing it because we've learned how to do things, as I will describe next. But here in the picture, I don't want to leave that picture without saying that you see here, the red is a charge. And the green, they show the arrows of a field that is created by this charge. If I apply the divergence of this field, we will see later that that divergence gives us important information. All right, so, but this is where divergence is used and is extremely important when it applies on a vector field, like the ones that we are dealing with in electromagnetics. Okay. Now, I wanted, before I give you the example, to tell you that I did the same here. I put in 3 rectangular frames, the expression for the divergence in the Cartesian, in the cylindrical, and in the spherical. Okay? And now I'm gonna discuss with you the following, or at least we'll have the following discussion so you can understand why the divergence has been very fundamental in our lives. When you have a quantity, so that our brain and the brain of all the species by evolution has been designed to do what? To spend the least possible energy. Do you agree with that? Because those animals or species that were spending a lot of energy, they did not survive it. All right, what means? If I spend too much energy, I need too much food. And there is scarcity of food in any environment. Always scarcity of resources. So the species that survived were the ones that evolution made work with the least possible energy. Our brain and the brain of the animals, especially the small ones where the brain is small, has fewer neurons, they've learned how to live in a way that the brain does not need too much energy. Number one. Okay, so what that means? When we see, I see this class right now. What do you think my brain does? My eyes receive all of the reflected light, all right? And on the basis of what frequencies have been absorbed, I see this white, because very few frequencies have been absorbed, and I get everything back, so it gives me that. I see this dark black. Why is that? Because the material is such that absorbs most of the frequencies. And then I see your colleague to wear a whatever purple lavender shirt. I see you wearing a maroon, and I see all kinds of other colors. And then what my brain do? It takes this information that goes through the eyes, the optical sensor, takes it to the optical nerve, and then processes it. So when you decide to raise your hand, then, thank you, my brain looks at everything, processes again everything, and then I see that your hand is in a different position, and then I understand that your hand is in a different position. Okay, now our brain, the human brain, is pretty large and has many, many neurons compared to other species. Let's look at the fly. Let's see how the fly, do you know how the fly sees? Have you tried to catch a fly? Is it easy? No. Why do you think a fly is not easy to catch? Because it's smarter than we are? Their brain is teeny. It has so many few neurons. Why can the fly see faster than we can act? But because the different angles are important to see everywhere. It's the space you have available, optical domain. What is what the fly does? And more other species too, similar insects. The fly does not see everything. The fly sees only change. The fly gets everything information, but the brain only looks at derivatives. The fly does not care for those who sit in the same place. If you sit like that, the fly will be everywhere, here and there. It will sit on your head. It will sit in your food. You know the whole thing. Doesn't care where you are. The moment you move, then it's gone. Why is that? Because it sees the change in the environment. It sees change. It does not record the permanent, what is not changing. And why is that? Because it's a lot faster to process change than to process everything. Smart, isn't it? So now people are creating cameras that they call it, camera that records everything is called the mammal's eye. All mammals have the same. And a camera that records only derivatives is called an insect eye. And to be more formal, we call it an events camera. And do you know who has an events camera that records only derivatives, like the divergence practically, things that you play with? Drones, especially the small drones. Do you know that there are these competitions where you design a drone and then the one that finds a hole to go through fastest is the winner? There are the whole competitions, the whole country goes there. I mean, those who are crazy with drones, they make their own. Why do drones, the fastest drone that my colleague was telling me was one from ETH. And one of a US government did a competition. Why were they fast? Why did this drone, the whole thing was for the drone to go around and find a hole like that. The drone was tiny. And find a hole like that, go through the hole, and then go through other holes and do inside a building and take pictures of something. So that was the plan. Their drone was the one that found the hole fastest and got in there because it was using an events camera and was doing all of the computations much faster than every other drone that had the traditional camera. Smart, isn't it? Why is that? Because if I have a hole like this, if I have a wall like that and a hole like this, the wall is going to be whatever color, the hole is going to be dark because there is no material in there. So the reflections are not the same like with the environment. So you see the hole. An events camera will see the perimeter of the hole because something is changing there as the drone moves. And so it goes in there fast. The flight does that. Okay? Really smart. Now you say, okay, the fly is smart, the drone is smart. What do we have to do with that? And I have to tell you that we do the same. We just don't call it that way. So that's my example here. Can anybody recognize that? What is it?
The Sistine Chapel,
Yes, it's the creation of Adam. So God shows to Adam and Adam is trying to. Okay, who did this? Michelangelo. Do you think that Michelangelo, especially his students, were doing most of that? He was like a master. He would say, put this there, put it down. And he had a lot of students, really. So what did Michelangelo do? Do you think that he was waking, like talking about the plans, all right? Do you think that he would wake up one day in the morning and say, we're going to do that, and he was going and doing it? No, he was planning on doing that. Do you know how many times and thoughts he had about how to have the hands? How did we find this out? This. Do you know how many of these Michelangelo did? Different hands until he decided to use that one up there? Okay. Now, do you think that every time Michelangelo wanted to try to do a hand, he would do a whole picture, a whole painting?
No.
He would have to be 1,000 years old, all right, to do this. So what did he do? He did a sketch. What does a sketch do? Outlines only the places where there is a difference, where there is a change of the value of, in that case, of the optical field. When you say, when you go to elementary school and then you say, could you draw to me a ball? Like, I have a granddaughter, she's 2. And she draws balls. Like, you know how she does that? Like this. This is the simplest way of drawing a ball. All of you did that in kindergarten or pre-K. What is this? What does that show? The real ball does not look like that, but this is a sketch of the ball. And what does this show? The place where there is a fundamental change in the optical field. That is the divergence of the optical map. So it is we have done it. When Michelangelo was doing this and he put some shadows, all right? He tried to do a little more. He did not do the fundamental. This, for example, the ball my granddaughter is doing is just like you look at the highest value of the derivative and it happens right around where the ball is described, the surface of the ball. But if you try to be and show a little more information about the derivative, you will see the other shades that you will do. This is plotting the divergence. Do you understand now why it is important? We have been doing it our whole life, but have you thought about this that way? That's what we're doing. So now remember it. And we do it because it's fast. It is fast to do that. You can do a lot of drawings before you do. I mean, when we do engineers, when I draw here for you a microstrip line, here. What is that? I'm drawing just the perimeter where in the optical field where the divergence has the highest value. All right? And I do this because I want to do it fast. Otherwise, I will have to draw there for a long time to do something realistic. So we use this all the time. And as a matter of fact, one more thing. Do you guys know about, how many of you know a little bit about artificial intelligence and machine learning? Have you taken any classes? Okay, my advice before you graduate, take a class in machine learning. By the time you're gonna be in your mid-30s, you will have to use machine learning someplace. So before you leave school, take a class, even in the summer or online or whatever. It's gonna be amazing. But in machine learning, because you teach the machine new tricks, practically. And then when you do deep machine learning, you provide the ability to the computer or the microchip to do what? To learn and change the data that it has, which are some coefficients, all right? How does it learn? By looking at the divergence, at the derivatives. Because the moment you look once for all of the values, like let's say that you need to teach your machine to identify like pictures. There's one scanning, it records all of the values. And then if the pictures change, it looks for change in those values. It does not record it again and then compare one pixel with another, with every other pixel. No, that would never end. So it looks at derivatives. Okay, that's the fastest way to be able to do computations. The last thing, and I don't know, the last thing for today is the curl operator. And then it's not exactly the last, but we're getting close to that. The curl operator is yet another expression of the del operator. When the del operator creates a cross product with a vector, it's called the curl, right? And while the divergence of a vector shows the change that is happening and where it happens, the curl of a vector tells you whether the vector rotates, all right? If the vector field is it's like an infinite flow, one direction from left to right, is called a solenoid. It does not have rotation. Even a solenoid that is kind of, say, when the field is inside its own bounds, even if may not be straight, but does not flow out of its shell, if you like, it's called a solenoid. But a field like the one from an antenna, and there are antennas that create different fields, then it may change its direction someplace. All right, it will not go straight, it will change its direction. Then we say that the field is rotational there, when it changes direction and start mixing up. And so I will show you some examples. But in any case, before we get there, I also did the same. I put the curl operator in 3 separate frames for you. And then that's exactly where now we're talking about, and you have to look at this to do also your quiz. And it is in the book. But here is why these are important. Let's start with the first one. A vector field that has neither a divergence or a curl, it's a solenoid that goes without any change in the same direction. It's called solenoid because like goes straight, all right? Without it, there's nothing changes, it goes. A field like this, so the solenoid idea is more like the current that flows inside the wire. The charges flow inside the wire like a solenoid. Now the field outside is magnetic, but it's not a solenoid, the outside field, all right? But the currents look like that. So there are electric fields that look like this, that have zero divergence and zero curl, and we will find them in the parallel plate capacitors, okay? When we are gonna try to calculate the capacitance, because these capacitance are extremely important for circuit design, for those who do circuit. The next one, is a field that is created by a charge. This field, of course, has a divergence, all right? So changes from one position in space to another, but it does not have a curl, so it's not rotational. It is not rotational, and it is not a solenoid. And usually these are the fields that are excited by antennas. Okay. There are antennas that will excite rotational fields, but this particular one, which is like, if you have a small, teeny antenna, it will look like this, the field. Then you have fields that look like that, which means, as I said before, it's a field that stays. I mean, if this vector field was a force, and if this force was moving a particle, then the particle will stay within its own orbit without interacting with another particle at a higher orbit. So this is still a solenoid, it's not straight, it's still a solenoid. So, however, it's rotational, all right? It's a rotational solenoid, which means that your divergence is zero. However, the curl is not zero, makes it rotational. Yes?
What was the definition of solenoid?
Solenoid is something like that it also always stays in the same trajectory. It does never gets out of it. And that is a solenoid, right? When the field disperses and rotates locally, but there's other things that it's rotational. It's not a solenoid. There is as an example, when do you think which field is a solenoid? The magnetic field from an infinite wire. Think about it, okay? So, and the last thing, when you have a field that is everywhere, like both divergence is not zero and the curl is not zero, so it's not a solenoid and it's rotational, all right? Now, these therefore are important. Why I'm using that is because you see now that we are developing math to explain things that we have been doing, but we never knew what we were doing. We're just doing it because we were taught, like drawings and stuff, right? But nobody explained to us what we were doing, all right? Nobody explained to us in the past why the fly is faster than us, even if the brain is teeny. And the other thing is we're developing math, because math, you see math and you understand physics. If you see math and get stuck with that, then there is a problem, because the idea of math for engineers is to use it. So you see math and you understand things. It's like when English for me is a second language. When I started learning English, and I was very young then, what happened is that I had to think every word. I had to think it and then put it in a sentence. And then when you were speaking back to me, I could not understand the meaning because I was getting stuck in the words. I was trying to think what every word meant, and then I could miss the meaning in the sentence. When you get familiar with it, even if I could not understand all of the words in the sentence, make sense of the meaning. So that's what we are trying to do, little by little, all right? Look at math always. When you see math, don't stop there. Ask yourself, what does this mean? If you don't ask the question, you will never be able to use math in a way that will help you do engineering, all right? So what does it mean is extremely important, always. You need to remember that. So the last piece, and from the book, if you go back, this is already uploaded. So number one. Number two, when you go back to this one here, you will see that I have told you what to read. So in here, 3.9 that you see, all right, that vector calculus and representations of fields. Representations of fields is 3.9. Look at my notes and read that and do the quiz. And it's gonna be easy. Yes.
Before Monday.
Okay. Before Monday at noon, whatever, afternoon. Yes. Question, speak up. You don't? I cannot hear you, I'm sorry.
I don't have a question.
Okay, thank you.
Sorry.
Yeah.
You said that it's 3.9.
Yes. Practically, we need to read whatever I'm giving you. But at least read 3.9 before you. My battery, we are done, so you can replace it. Thank you very much.
Professor,
Turn it off also.